We previously went through how to use Gaussian elimination to solve for systems of equations, of systems of algebraic equations. Now we're going to talk about characterizing systems of those algebraic equations. And that means how many solutions are we going to get? The possibilities are 0, or exactly 1, an infinite number, or no solutions. And if there's an infinite number, how many free parameters? We already talked about what free parameters are. So now we're going to get into how do you characterize the system without necessarily solving for it. Before we get there, we need to talk about matrix rank. And to talk about matrix rank, we need to talk about linear independence. First, let's talk here. Let's say we have this as a starting matrix. And we'll talk about row matrices made up of the rows of these matrices. So this little row matrix is just this top row. This matrix is that middle row, etc. In this case, what if I took 4 times row 1 and subtracted half of row 2 from it? Here's what it means. In arithmetic, it says you get 3, 5 minus 7, 8, which happens to be what row 3 is. So row 3 is a linear combinations of rows 1 and 2. Or I could express it this way. They are linearly dependent. I could express any one of them in terms of the others, in terms of a linear combination of the others. We say they're linearly independent. If the only way this expression is true is if all these coefficients C's are zeros. Think about that a little bit, and it's the same as this. If this is true, then or if this is true only if all the C's are 0, that means none of these R's can be expressed as a linear combination of the other R's. They are linearly independent. So that's the concept of linear independence. And from that, we can define what we mean by rank of a matrix. Rank of a matrix, denoted by rank A, it's the maximum number of linearly independent row vectors of A. It happens to be the same as maximum number of linearly independent column vectors of A, but they're the same thing. So let's take these as examples. This one's obvious. Row 2 is just twice row 1. They're not linearly independent. In this case, I can come up with row 3 as 7 times row 1 plus 20 times. They're not independent, they're dependent. What about this guy? How can I check that in that case? Well, let's try our definition. If I took those 3 rows and multiply them by these coefficients C1, 2, and 3, I would just get this row vector, C1, C3, C2, right? That's going to be all zeros, or the 0 matrix, only if all 3 of these are zeros. So those are linearly independent. That seems like a hard way to do it, right? Here's the beauty of it, though. And I'm going to have to just state some theorems without proving them, because at least one of these is pretty difficult to prove. The non-zero rows of a matrix in row echelon form are linearly independent. Theorem 2 is that row operations preserve the rank of a matrix. With those 2 theorems, we can say the rank of a matrix is the number of non-zero rows when we get it into row echelon form. So here's our method of finding the rank. we don't have to go through this sort of logic every time. We use Gaussian elimination to put a matrix in row echelon form and then just count the number of non-zero rows. Here's a couple other facts. If a matrix of all zeros has a rank of 0, any other matrix has a rank of at least 1. So the 0 matrix is the only rank 0 matrix. The rank is no bigger than the smaller dimension, either the number of rows or the number of columns. You don't have to do complete Gaussian elimination. We'll talk about that a little bit. So I don't want to go through all this arithmetic again, but let's say we started here. What's the rank of this matrix? Well, we do row operations. Gradually get it in row echelon form, or almost row echelon form. I didn't divide this guy by 2, so there's not a 1 here. I didn't multiply this guy by 3/2, so I don't have 1s. Pivots are not 1s. It's not technically row echelon form as I defined it previously. That's good enough because those little multiplies give us a similar result. All I care about is how many non-zero rows are there. 1, 2, 3. We've got an all 0 row. So the rank of this guy is 3. You can't just look at it and know. So now let's apply that, characterizing systems of algebraic equations. And now we're talking about augmented matrices. Rank applies to any matrix. They don't have to be augmented matrices corresponding to systems of equations. But now we're talking about that. We talk about the rank of the A matrix, to the left of this line here, the rank of the whole augmented matrix, and N, which is the number of columns of A, which is also the number of variables in the original system of equations. So let's talk about those 3 things for these different, these are different examples. Here, the rank of A, the A part is 3. The rank of the whole A augmented matrix is also 3. And N equals 1, 2, 3, the number of columns of the A part. N equals 3. So we want to calculate those 3 things for any augmented matrix. What about this? Rank of the A part is just 2. Rank of the whole augmented matrix is also 2. N again equals 3. Here, let's see, I have rank of just A part, that's to the left of this line here, is 2. The rank of the whole thing is 3. Again, N equals 3. And what about this guy? The rank of the A part is 2, so is the rank of the whole AB augmented matrix. And N equals 1, 2, 3, 4, 5. We just did those little calculations. Now, how do we characterize a system of equations from those 3 things that we determined from the augmented matrix? And for that, I use a decision matrix. Hopefully, you've seen something like a decision matrix before. These top 2 rows are conditions. Bottom 3 rows in this case are the things you do, or the answers. So if the rank of A equals the rank of the whole augmented matrix, I could either have a yes or a no. Actually, there's 4 possibilities because I have 2 yes/no questions. The other one is the rank of A equal N? You have either yes or no. This could be yes or no, but it's going to turn out it doesn't matter. Top thing is a no, I'm going to get 0 solutions. rank A does not equal rank AB, I get no solution. That's an inconsistent system. If rank A equals rank AB, and it also equals N, I get exactly one solution. And if rank A equals rank AB, but it's not equal to N, something less than N, then I get infinite number of solutions. How many free parameters? It'll be whatever N minus the rank of A is. So let's go through those 4 examples. This one, the ranks were equal and they equaled N. I'm going to get one solution out of this system. Here, the ranks are equal, so I get solutions, but the rank was 2 and N was 3. So I'm going to get an infinite number of solutions. How many free parameters? 3 minus 2. N, or the number of columns of the A part, minus the rank. And what about this guy? Rank of the A part was 2, the rank of the AB part was 3. They're not equal, so I get 0 solutions. That's an inconsistent system. This guy, the ranks were equal, but the rank was 2, N was 5 here. So I get infinite solutions with 5 minus 2 equals 3 free parameters. And that's how you characterize a system of weighting. Try to go through these other examples really. So here's our given system. Ooh, this guy's homogeneous. By the way, if you go through that decision matrix, think about it. If it's a homogeneous system, this right column is always going to be all zeros. So the rank of A will always equal rank of AB. You either have exactly one solution or an infinite number of solutions. And if it's exactly one, it's the 0 solution, all zeros. Oh, here's the first. Here's the given system. This one's not homogeneous. We converted. I didn't put the line in here, but after you do a few of these, you put that in your head. So I could do row operations, get into here is row echelon form. A part is these left 3 columns, has a rank of 2. AB is all of it. It also has a rank of 2. But N equals 3. 1, 2, 3. A part is the left 3 columns. B part is always that right column. So I'll have an infinite number of solutions and 1 free parameter, because 3 minus 2 is 1. I'm not going to go through this. This one's homogeneous. Let's see. Here it is in augmented matrix form. Do my row operations. Here it is in row echelon form. Rank of A equals 2, rank of AB equals 2, but N equals 3. So again, I get 1 free parameter, an infinite number of solutions. Won't go through this one in detail, but original system, a bunch of row operations here. As soon as you see this, remember the right column is the B part. Everything to the left of that is the A part. This means that this, let's see, 1, 2. Well, this means 0 equals 1, which is an inconsistent system. I don't have to really go through that decision matrix. As soon as I see this, I know I have 0. All right, that's characterizing systems of algebraic equations and matrix rank for its own sake.